my great pleasure to introduce this evening's speaker. So this is one of our distinguished lectures where we ask one of our leading academics to talk to you a little bit about their research in the style of a public lecture, so you become aware of what we do at the university. So this evening it's my pleasure to introduce Professor Danielle George. Now, I know Danielle extremely well. We've done research together in the same department of electrical and electronic engineering. Danielle's expertise is very much focused around radio systems, and she's a professor of radio systems engineering. So she's been leading world research in the area of producing what are called low noise amplifiers. So imagine you want to amplify a very tiny signal from a long way away in a distant galaxy. This is the person you would come to work out how to do it. But as you'll hear tonight, she also does a lot of work a lot closer to home around sensing systems around gas turbine engines to improve fuel efficiency, or around agriculture. The title of the talk I think is quite interesting, Engineering Difference Makers. And I think it's interesting for two reasons. One, my personal opinion, she is one of the difference makers. And secondly, through talks like this, she's going to try and create the next generation of difference makers, which I hope is you. So would you all help me welcome Danielle to the stage?
Thank you. Thank you very much. Thank you, and welcome. I'm very much looking forward to chatting to you today, but also the questions afterwards. So have a think about any questions as I'm talking along the way. I'd love to get some questions at the end as well. So as Peter said, what I'm going to talk about is engineering difference makers of the past, present, and future. Engineers, difference makers, they've made a difference throughout history, and they'll continue to do so. They certainly have made a huge difference in Manchester, and well done everyone for making such a brilliant choice of university. This is a great city. It is vibrant, it's lively, it's very cosmopolitan. It has a very, very rich history in terms of the Industrial Revolution and sort of the birthplace of quite a lot of engineering and technology in the past as well. The reason I'm showing this is because I'm an engineer at Manchester, and it's because I'm at Manchester that I can do what I do in my research. It's really important to me, the facilities we have, the research team, all of the support. That's why I'm in Manchester to do what I do as well. And like the title of the talk says, engineers are difference makers as well. And I want to put some difference makers up, some engineers, difference makers. And I want you to put your hands up if you know who they are. I'm not going to ask you, don't worry. But just put your hands up if you know who these are. Yeah, Steve Jobs. Yeah. It sort of gives it away with the phone that he's got in his hand there. But yeah, Steve Jobs. What about this one? Oh, good. Wowzers. Okay, Nikola Tesla. He is just the dude. Anyone who does anything about science or engineering, you should get to know this man. He's brilliant. For those who don't know, he gave us alternating current, AC current. He did the so-called battle of the currents with Edison, and he was such an amazing difference maker and an entrepreneur as well in his time. He thought of the Apple Watch in his time. So, 120 years before we all got the Apple Watch, he was thinking of a watch, of a small thing that would be able to send signals, be able to send messages, send pictures, play music, etc. So he had these thoughts in his head hundreds of years before we got them. What about this one? Good. Oh, we're doing well. Blimey. Okay, Elon Musk, Tesla cars, and CEO of SpaceX as well. So we know him as well. And we make such a big difference in the world, but also to our lives every single day. Does anyone know who this is? This is hard. Oh, do you know who this is? I might ask someone. Put your hand down. Go on. Yeah. Do you know who it is?
She's the one who mostly, right, is the one behind the car.
With the car, windscreen wipers in the car. Great work, well done. Blimey. Mary Anderson, yeah. So she invented windscreen wipers. Try being in Manchester without them when you're driving. What about this one? Oh, I thought maybe more people would know. Yeah. This is Ada Lovelace. Now I've said that, do you know who it is? maybe different pictures. Ada Lovelace is definitely the pioneer of modern computers. So she was thinking about a machine that could process musical notes, it could process letters, images, and this was, again, 100 years before we have the modern computer as well, so massively ahead of our time. What about this incredible mind? Oh, yes, good. I'm glad somebody knows. Who is it? Hedy Lamarr, excellent, thank you. This is Hedy Lamarr. Everybody should know who she is, and hardly anybody does. She has given us secure Wi-Fi, GPS, and Bluetooth. Imagine your lives without those now. She's given us all of those things. She was a phenomenal actress as well, which is why quite a lot of people know her. But actually what she gave us was secure Wi-Fi, GPS, and Bluetooth as well. Huge, huge difference makers. These people are, the 6 people I've just shown. Imagine your lives without the things that they've invented or developed as well. And, there's so many challenges that we can work on. Some of them small, some of them really, really big. And they can be anything from engineering better medicines, they could be reverse engineering the brain, it could be providing access to clean water. There are 14 world engineering grand challenges of the 21st century, and you can see them on the screen here. And I work on one of these. I work on, I can show you, this one here, this little microscope down here, which is engineering the tools of scientific discovery. So I do that, as Peter was mentioning before, for a range of different projects, and I use radio waves to do that. So I'd like to take you through some of the projects that I'm very privileged to work on. But what are radio waves? I'm aware that maybe not everybody knows. What you see here is something called the electromagnetic spectrum. So whether you're sitting at home, sitting down here today, walking down the street, you are bathing in a sea of electromagnetic waves. So these undulating particles with no mass called photons that zip-zap invisibly through space at the speed of light. And these photons have different energy depending on where they are on the electromagnetic spectrum. So the bit that I work on is here on the electromagnetic spectrum, the sort of radio and microwaves part. And this is the sort of long wavelengths. So this has less energy. As you get to the higher wavelengths, you go through visible light, and then you get to the X-rays and the gamma rays. The short wavelengths have a lot higher energy. And so everything we do in terms of transmitting data is somewhere on this electromagnetic spectrum. And now we move through life with so much data and this sort of broth of energy that you see on this electromagnetic spectrum. And we're using this energy to transmit data around the world and around this room right now as well. And data is such an important commodity now. Imagine your lives without data. We mine it like coal. We store it like gold, and we sell it like a rolled steel. And it's so important for us now as well. And there's a huge amount of data out there now. Every 2 days, we create as much information as we did from the dawn of humankind up until the year 2003. And that's according to Eric Schmidt of Google fame. And that's something like 5 exabytes of data. So let me just repeat that. In the past 2 days, we have created as much information as we did from the dawn of civilization up until the year 2003. Huge amounts of data, and that's only going to get more and more as we all are using more and more data, and we get to 5G and 6G and all of the other fast data that we have as well. And it is huge and in such an important part of our life. But what is data? I mean, fundamentally, what it is. I'm an analog sort of person. Peter is the digital person. Basically, it's just a bunch of ones and zeros. That's all data is. Ones and zeros in the digital world. But a physical system, if you think about a physical system and think about it in the digital world, you can represent that in bits. You can represent any physical system in bits. but that must be limited. You know, it's not, you can have sort of an infinite amount of bits. And this sort of limit is something called the Beckenstein Bound. Now, bear with me here. So what I'm saying here is if a system's mass, energy, and dimensions are known, this Beckenstein bound that you see here defines that maximum number of bits that would be required to recreate any system in the universe perfectly. So if that's true, we should be able to recreate the most complex system in the universe. Does anyone know what the most complex system in the universe is? Yeah.
Would it be the brain, maybe?
It is the human brain, yeah, well done. So if this is true, we should be able to calculate in bits what the total information content of the human brain is. Does anyone want to hazard a guess as to what that would be, what number that would be in bits? Big, that's what it would be, really big. About 2.6 times 10 to the 42 bits. That is the total information content of the human brain in bits. And it's quite a sort of a big number to think of. Think about it in this way. If you converted the brain, if the brain was expressed as a song, and you downloaded that song and played that song would last for 50,000 trillion years. That one song. So it better be a good song. And we're using data now to connect instruments and literally sort of instrument the world now. And it's having a really, really big impact on the way we farm, the way we fly, the way we design cities, and so much more. For instance, there are 2.8 billion people still affected by water scarcity in the world. And that number is only going to get bigger as the need to feed an increasing population also gets bigger. So there are several people working on wireless systems, wireless sensor networks. And this is a project that Peter and I have worked on with our PhD students and our postdocs as well. What we were trying to do here was try and preserve that very precious resource, water, and only use it where we need it in farming. So what we were doing here is the node, this node down here, has some sensors in it, and the radio frequency identification circuit, and then a little antenna here, okay? And those sensors would be looking at the soil temperature, looking at the nutrients needed for crop growth. And so what we would do is put these sensors in the ground, in the soil, in a field, and of course they can't be wired because that crop, you know, the crops are there and the field is going to be harvested at some point. So, you know, you don't want a tractor coming across and breaking all the wires. So they have to be wireless. The other thing that they have to be is to be able to get their energy from somewhere, because you can't put a battery in this. You don't want to be able to contaminate the soil in any way by, you know, a battery leaking into the soil. So it has to be able to harvest the energy from somewhere. So that's what it's trying to do here. So it's harvesting the energy from the actual tractor here. So what happens is there's a number of nodes in the soil. The tractor comes along. On the front, it has the sensor and the antenna, and it's reading the information from all of those sensors. So it's not only is it giving power, but it's reading the information from those sensors as well. And in real time, it then on board the tractor, it can tell the farmer that bit of soil has enough nutrients, enough water, etc. Don't water this bit. Or this is looking pretty dry, water it. So instead of a farmer just irrigating the whole of the field, you're now just using that very precious resource of water just where you need it. And that's really, really important in any country around the world as well. So we're shifting towards this sort of model of precision agriculture using wireless sensor networks and a lot of data as well. Now consider something a little bit bigger, an industrial gas turbine engine. This is the one from Rolls-Royce. Again, Peter and I had many a happy time working on these amazing, just beautiful gas industrial turbine engines as well. What we were trying to do here was, so during the development of these huge engines, they are instrumented with a whole bunch of different sensors. And so those sensors want to look at the temperature, the vibration, things like that in the engine. So during its development, there's lots of sensors put on, but they're all wired. Now that's fine, except there could be kilometers worth of this wiring. They're quite hard to set up, so you need to be very well trained to be able to set it up. And also they could be susceptible to cable and connector faults as well with all this wiring. So what we wanted to do was remove all the wiring, make it wireless sensor networks on the engine. So you imagine sort of the size of, I don't know, maybe between a mobile phone and that sort of size, these sensors, and you put them, as many as you like, round the engine. And they all talk to each other, and they're all collecting that information, and then they wirelessly send that information out, so there's no wires anymore. It's a lot easier to set up. You don't need to have a really experienced person doing it, and you can put so many more sensors on there and get so much information about that engine. Why do we want to do that? If we know more information about that engine, we can design more efficient engines in the future, so we can start to try and reduce carbon emissions in the future by using wireless, by using radio, and again, a lot of data as well. Now, let me go even bigger. Big scale, big data instruments. We've been looking at the universe, sending radio waves into the universe for 100 years now or more, and listening back for about the same time. And that's allowed us to understand how much of the universe there is that we just don't know about yet. So in the past few decades, larger and more powerful radio astronomy instruments have been developed to look deeper and deeper into the universe. And me and my research team are very, very lucky to work on two different projects. The first one is called ALMA, the Atacama Large Millimeter Array. Now, this is a revolutionary instrument in its scientific concept, but also in its engineering design. It is amazing. It's in Chile. It's 5,000 meters above sea level, and it has 66 of these very high precision antennas that you see now, sort of big dishes that you see up there as well, and it's working at a higher frequency. It is so sensitive, it's going to open an entirely new window on the universe and allow astronomers to unravel some really long-standing mysteries of the universe as well. I want to show you a quick video of what ALMA can see here. So this is a video sequence, and we start with quite a broad view of the southern sky, and it starts to zoom in to a very faint constellation, which we call the Clock. And as we get closer to this constellation, we see quite a striking spiral galaxy right in the middle there. And that spiral galaxy has a very catchy name of NGC 1433. And it has, the central part of that has a supermassive black hole in the middle of that. And observations of this supermassive black hole and all of its surroundings have discovered the sort of a spiral structure, a new molecular gas, as well as some newly formed outflow material. You could not get an image of something so far away without using something like ALMA. It is just showing us completely new things about the universe as well. And it is revolutionary, and it's, like I said, from a scientific point of view, that's brilliant. The thing that I absolutely love about it is the engineering design of it as well. So this is how the dish works. What you can see over here is something called the cryostat. So this is sort of the receiver, the big fridge. So we cool everything to 20 Kelvin, which is what, minus 253 degrees Celsius. And that's so we don't capture any additional noise. We just want to see the signal. We don't want to see any interference. We don't want to see any noise in there. So what you see is the incoming signal coming into the dish. It gets focused. The red thing that's flashing there is the thing that I work on. Like Peter said before, I work on the amplifiers, so that's in the front end, and we cryogenically cool those amplifiers. And they're about 1 millimeter square, these amplifiers that we design and test. Then we convert it, and it's all put into, all of the signals from the 66 dishes are then put into a correlator, so they're all the signals are put together and then sent, this huge amount of data sent around the world for astronomers to work on and use their observations. With ALMA, the supercomputer that's there is the highest supercomputer, operates at the highest altitude in the world. ALMA has 10 times more detail than the Hubble Space Telescope, 10 times more detail than the Hubble Space Telescope images. 17 trillion operations per second are needed. So that's 17 peta operations, 17 trillion operations are needed for this. It's the fastest computer ever used on an astronomical site. But just things like, on the correlator that you see there, there's 20 million welding points, 20 million. And all of this must work at exactly the same way, no matter what the temperature. And remember, this is 5,000 meters above sea level in Chile, where day and night temperature can range between 30 and 40 degrees. And all of that has to work exactly the same thing. The dishes themselves, the parabolas, the dishes, don't deviate from more than 10 microns, more than 10 millionths of a meter. It is superb engineering, and the people who work on this are complete difference makers. And we are really pushing the boundaries of semiconductor technology in what we're trying to do with this as well. I just want to show you this image. This is an image that was taken, it's a couple of years ago now. This is of a young star, and what you're seeing, so it's about 1,500 light years away. It was a collaborator of ours who worked on this, and they took this image with ALMA, and what they found when they observed it was they had something was glowing around it, and they weren't quite sure what it was that was glowing, and it was salt. Sodium chloride, just normal table salt, glowing around a star 1,500 light years away. And so me and my research team were like, wow, that is amazing. Why? Why is it glowing? And they were like, I don't know yet. We just don't know, because we didn't know it was there until we had ALMA to show us that young stars can glow salt, ordinary table salt. And I think that's what's lovely about quite a lot of the work that my team work on, is we just have unknown quantities. We don't know all the answers, and that's what's really, really nice. The unknown brings me to the next telescope I work on, I've worked on in the past. It's called the Square Kilometre Array, or the SKA. Now this is a completely different type of telescope, and you can see an image here of it. It's going to be in Western Australia and in South Africa, and all of these dishes and these aerials, these dipoles, are going to be connected all together between Western Australia and a remote area in South Africa as well. It's currently being built, but when it's built, it will be 50 times more sensitive than any other radio instrument in the world. It's going to be the largest science facility ever built by mankind, humankind. And it's revolutionary, completely different to ALMA, very different frequency, very different setup, but revolutionary in it. So what you can see is there are these dipole arrays that you just saw, and then also some dishes, so they look a little bit more like ALMA radio dishes here. It's going to address very, very key and ambitious questions in astrophysics, in cosmology, and fundamental physics. One of my favorite facts about the SKA is it's going to be so sensitive, it'll be able to detect an airport radar-like signal on a planet 10 light years away. Very, very, very sensitive. You know, it is such an amazing project to work on. It brings thousands of scientists and engineers together around the world who are making such a difference when they're working all together as well. I just want to give you some facts about the SKA. So the low frequency, so these sort of dipoles, like you might have seen as sort of the old-fashioned antennas on the top of houses, there's going to be thousands of them, absolutely thousands of them. And when they're all connected, the amount of data that they're going to collect could be up, so the amount of data they're going to collect in one day could be up to 5 times the global internet traffic. 5 times the global internet traffic. If we could express the data, the SKA data, collected in one day and download that as a song, the song would take 2 million years to play back. And that's the data from 1 day's worth of collecting. Huge amounts of data in this. The high-performance central computer that's going to be needed here needs to perform 10 to the 15 operations every single second. Terabyte images are going to be needed to be transferred worldwide every single second. If it was built now, though, so it's being built, and we're building 10% of it at the moment, and it's going to take, you know, another decade or so before the whole thing is built. If it was all built now, we'd have to throw away 90% of the data because there literally isn't the computing power in the world to store all of this data. How tragic would that be? You know, you have to throw away 90% of this data. So the only thing the astronomers would really be able to keep is the thing that they think they want, they think they're looking at. But all of this stuff over here that might have the most amazing observations and the most amazing answers about the universe, they just have to throw away because we literally do not have the computing power in the world. And, you know, for me, that's probably not going to be solved completely in my lifetime. And that's quite an interesting thing to work on, you know, so you know that there are challenges that are going to outlive you and your own career. So who's going to be working on it? You know, we need difference makers, we need engineers of the future to work on this as well. But we all know there are issues of shortages of difference makers, so shortages of people who work in technology, shortage of engineers. And I just want to pause really just to think about why we've got this problem. Because I feel really lucky to work in a profession where I can look forward and see the rising demand for my skill as well. And it's interesting, you know, how great would it be to be in an industry where people want to join because they know all of the great opportunities there are in science, technology, engineering, and maths as well. And, you know, society, including very young children, have an understanding of what many things do, like medicine, because we've all had first-hand experience of it somehow, so we manage to sort of understand it a bit more. So it's ironic, I think, that engineering is just everywhere, but it's invisible because it's woven into the very fabric of everyday life. Imagine your lives without engineering now. You just couldn't. It would be a very, very different life. And many people do not know what engineers do because it is invisible. But also, why should they? If we aren't out there telling people how brilliant engineers are, how ingenious they are, what a difference they're making to the world around us as well. So I think it's our responsibility. It's mine, it's Peter's, it's all of the engineers, the scientists in the room today, to make sure we do tell other people, we do share our passions about the work that we're doing. It is really, really, really important. What's also important is that you share your failures with people as well. It is super important to share your failures as well and to get out of your comfort zones. So no matter what you're going to study here at Manchester, get out of your comfort zone. It is where the magic happens. You feel really safe and you feel really comfortable in your comfort zone. You're not innovating, you're not thinking in the best way until you're out of your comfort zone, and that's where the magic is happening as well. And that doesn't mean you have to succeed all of the time. You will fail along the way, and that's good. It's not just okay, it's good. What's important about it is that you share those failures as well, and we celebrate the failures. They are fantastic. I remember I used to teach first year electronic circuit design to our students in electrical and electronic engineering. And I always used to say to them, we need to celebrate our failures, it's really, really important. And eventually a couple of our students were like, oh yes, Danielle, the smell of a burning resistor is the smell of success. Like, yes, it is. It absolutely is, because we should celebrate the failures as well, and we definitely should get out of our comfort zones as well. They are part of being an innovator and part of being a difference maker as well. And difference makers, we've all got, every single one of us here, we have some learning habits of mind that you will, if you haven't used them already, you're certainly going to use them when you're here at university. We're good at curiosity. You're all going to be curious about your own subject. Brilliant. Resilience, build up your resilience. Do fail, do celebrate those failures, learn from those failures, but you're going to build up those failures. You're going to adapt, you're going to problem find, you're going to creative problem solve. And these are all amazing things. We are going to solve those global grand challenges that I showed earlier by doing these things here and having these habits of mind. And we hear a lot in science, technology, engineering, maths about artificial intelligence, don't we? You hear an awful lot about AI. What about HI? What about human intelligence? It's amazing. AI is fabulous, don't get me wrong. But HI can define, it can modify, and it can build new forms of intelligence. HI is unique. It defines us as humans and our relationship with everything in the universe. So don't forget how important your HI is as well. We have these habits of mind that make us intelligent humans and that make us difference makers as well. So it'll take engineers of the past, the present, and the future, you guys, to solve the grand challenges as well. And all difference makers, whether that's engineering, whether that's in a humanities subject, whether it's in a medical subject, it's key. Difference makers, you difference makers, are key to safeguarding the health of our planet and beyond, and the rest of the universe as well in the years to come. Change is possible, and all of you can quite literally be the architects of that change. So I really want to see you, some of you, be the disruptors of the future as well, solving those problems of tomorrow. And I think you've all made a great start doing it by coming to Manchester. Thank you very much for your time.
Thank you very much, Danielle. I'm sure there's some questions from the audience, so who would like to go first, please? Yes, please.
With the square kilometre array, with all of this data that you're going to use, how do you expect the progression of computing to help with this? It's like, is the data present going to be suitable for use with quantum computing, which is starting to appear right now?
Yeah, great question. Quantum computing is going to be sort of the saviour to this. That's what we're hoping for anyway. It's the only thing that we can see on the horizon that will be able to deal with the amount of data we've got. So there are lots of people working on quantum computers, not only for radio astronomy, but lots of other sectors. And what I think is really nice is I'm seeing quite a lot of people working together on that. So it doesn't matter if you're not doing radio astronomy, you might be doing something completely different, but they're sharing the ideas and knowledge, certainly about quantum computing. So yes, quantum computing hopefully is going to be the saviour for this.
Thank you. Very good question. we have another question, please? While you're, oh, yes, thank you, please.
So what I found really interesting was the NACL around the galaxy that was glowing. So do you have any theory about it? Could it be some high density electromagnetic waves that are bouncing off the NACL and producing invisible light waves?
Do you mean the one that was the NGC 1433 or the young star that was glowing salt?
Glowing salt.
The glowing salt, yeah. The glowing salt one's really interesting because the astronomers still don't know what it is. Or actually, I stand corrected, they didn't know. This was sort of pre-COVID that we talked about it, so I haven't really spoke to them in the past year or so. So they might have discovered it. But I mean, they were sort of saying it's completely new. It's not what they expected to see at all, and they have to work out, is that important? Is it just a byproduct and it's not really a thing, or is it the fact that sodium chloride is, around a black hole? Is that normal? Do you get all black holes that have got sodium chloride? Does it have to be a certain amount of way away, like you say, to be able to see it from the Earth? So the last time I spoke to them, they didn't know. But they might know now, actually. So how could you find that out? I'll go back to that slide, and there's some information at the bottom of the slide. Maybe if you take that, and oh, there they are. So have a look at NRAO, AUI, and NSF. Oh, and his name's just off the side. And you should just Google it, and you should be able to find something on it. But yeah, it'd be interesting to see if they've found any more in the past year or so. Yeah.
Yes.
If we go back to the small data collector, which was about the agriculture. So when the tractor goes through like the sensors or contact with the sensors, within that be a little bit of disruption for the soil, or has no effect?
Would it be what? Sorry, for the soil?
Like when the charging current or whatever it is goes through the soil into the sensor.
Oh, do you mean
that create destruction, or it is like I don't know, without effect or something?
do you mean does it affect the soil?
Yeah.
Right. So no, it doesn't affect the soil. The challenge though is this might only be 1 meter or 2 meters, but trying to wirelessly communicate between, the wireless link between onboard on the tractor and the sensor node, I have found it just as hard to do that as I do for looking, 1.5 million kilometers into space, because the soil can change. So it's depending on how dense it is, how wet it is, it affects how well you can connect. So it doesn't, the actual sort of energy itself isn't really high power in that way. The sort of high power sits on the tractor, so it doesn't affect the soil, but it's really, really difficult to do it just, between 1 and 2 meters. And like I say, very, very similar challenges to actually trying to go millions of kilometers out, but it doesn't affect the soil. Does that answer your question? Yeah, cool.
I might have a question there. I think one of the challenges for engineers is we're not seen as creative. What do you think we can do to sort of change that perception that I think it's a hugely creative, I mean, what you've shown us is hugely creative.
Yeah.
What can we do then?
We've got to show, and it's all of our duties to show how creative it is. And I think we do it by sharing our passion as well. I think sometimes there's an image, isn't there, of a scientist or an engineer that's very, very sort of serious, and we don't laugh, and you can't, you have to wear certain things, or and we have to sort of smash those stereotypes. I think that really helps. I think also showing the engineering in the different creative industries is important. So, you know, the engineering that's in the fashion industry, that's in gaming. That's really important, I think, to show where the engineering is. So rather than getting people to come to us, we go, well, do you know, like, look at the fashion industry, how much engineering is in that? Gaming, you know, so music, you know, things like that. So I think we need to show how much engineering is in the creative industries, as well as showing, you know, how creative we are and showing our passion and sharing our passion for our work.
So if you could just do this talk about 20 million times. Thank you. Is there another question from the audience, please? Yes.
How do you power those sensors, recharge those sensors?
How do you?
Recharge those.
This was your area, Peter, the sensors, wasn't it? Yeah, it's a challenge.
Dare I answer?
Yes, of course.
No, yeah, so what you have to do with this is you've got to, I use the word illuminate. Danielle talked about the radio spectrum, the whole spectrum. So you're effectively from the tractor illuminating, it's a bit like shining light, through the soil on the sensor, and then it has to store the energy it's scavenging in order that you can then wake up the light and control the power the sensor, make the measurement, and transmit it back. Sounds so simple, doesn't it?
It does, yeah.
The PhD students spent 3 years developing a system that would work through about 1 metre of soil. But yes, I can't see where you're thinking, where's the power come from? The only place it can come from is the tractor. And so, as I say, it's a bit like shining light on the solar cell would be the equivalent. You've got to get enough energy into the ground to actually get and harvest that power. Yes, I think there's another question across here. Yes, please.
I've got a question about the concept of engineering like different sectors. So like, in your opinion, do you feel like us as engineers, should we be like specialists or generalists or like polymaths? Because you mentioned about stepping out of the comfort zone as well. And I think like in most future developments, they are often like intersecting different areas. So like, do you feel like we should be, are we like better positioned as like generalists or specialists to make the difference?
Yeah, that's a great question. And I imagine if you asked, you know, me, Peter, and if there was, you know, 10 other people, you might get 10 other different answers as well. From my point of view, I think it's really important still, you know, I work with industry a lot still, and what industry still want are domain specialists, you know, so they want the electrical, the electronics, the mechanical, the civil, the chemical, etc. But then what they also want is just a bit of that sort of systems thinking. So to still have that domain speciality, but then to be able to sort of take yourself out of that, which might take you out of your comfort zone, and see that sort of more systems approach to something. And I think that's where the likes of Peter and I and the other lecturers that you have a duty to be able to make sure that during your university time, you get both of those things. And the way that we'd like to do it is during project work, because that's sort of what you do in industry, you know, you know, when you graduate, you might be the domain specialist in you know, let's say electronics, but you're going to be working with mechanical, with chemical engineers, with scientists, with, you know, so with social scientists. So to be able to try and put you together into project groups where you can be the domain specialist, but still try and see that sort of systems approach, I think is really, really important. So generally domain specialism, but a bit of that systems thinking would be what I would do. But like I say, it'd be really interesting if you ask your lecturers as you go through the years and see what they think as well.
Yeah, I was reading an article like quite a while ago, to be honest, but it was talking about how they use like piezoelectric like cells in those cat eyes on the road. So like vibrations from the cars on the road, they charge those cat eyes, and I was wondering if you could use a similar principle to this. But is like, are the sensors too deep in the soil for like the tractor to have any?
For the piezoelectric sensors as well. Yeah, they're sort of quite a different setup. And I guess what do you think, Peter? I mean, I guess the depth is very different as well.
Yeah, I mean, I like your thinking. I think that's really good, which is, but if you think about a car hitting that and worked out how much energy is stored in that impact, and if the piezo can extract 20% of the energy, I think the problem is if you wanted to create the same displacement in that sensor and move it down from the soil, wouldn't like to think the
Yeah.
forces have to apply on the surface.
It's probably
So-
just a bit too far down, isn't it?
Yeah, but your thinking's really good because it's what the research student had to do. They didn't start their project again,
Yes.
it has to be radio. They started with the bigger question is, what energy could I get through the soil to power the sensor? But you can see why, if you were looking at, as you say, a cat's eye, piezo is perfect. You've got a lot of mechanical energy, it's regular, and it's there at the right time.
Mm.
So when cars are passing over, that's when you want the cat's eye to illuminate. Yeah, I wouldn't like to think the thump you'd have to put on the soil surface
Yeah.
to get the same amount of energy through to the sensor. But that kind of thinking is really good.
Yeah, really, really
So
good.
that when Danielle said think outside your comfort zone, that's the right way. You start to ask those questions, don't just assume.
Yeah, absolutely. Great question. Yeah.
My question is a bit more general. What do you think is the number one advantage of studying engineering in Manchester?
Of studying engineering or studying engineering at Manchester? Second one, okay. I think what you get at Manchester is the breadth of all the different type of engineering, but also the depth as well. So you might have other universities who are brilliant, let's say, at robotics, you know, and they are the place that you might want to go if you do robotics. But, and it sort of goes back to the previous question on domain specialism, if you might change your mind as you go along, if you want that bit of systems view, it's going to be very hard if you're in that university that just does, you know, one specialism. What we do at Manchester is a huge array. You know, we have the whole spectrum from really high voltage to, you know, really low current to, you know, mechanical moving parts on robots to artificial intelligence to, you know, the chemical aspects of it. And that, it's very hard to get elsewhere. So that, and the depth of the research that goes on here as well, it would be very, very hard to get elsewhere. Not completely unique, I wouldn't say, but very hard to get elsewhere. I think another great thing is so there are some universities who are very engineering specialist, who don't have as many of the sort of science or the social science, the humanities, etc. I think that's a really good thing for us, as we do have that breadth generally, where, you know, Peter and I as engineers, you know, I've just come from a meeting with two astronomers that I work with in the science, and so we have really good relationships with other specialisms as well outside of engineering, and I think certainly from a research point of view, which hopefully then informs our teaching to make sure that we're, you know, teaching students the most up-to-date things, is a really good thing, because we can get other people to give different perspectives as well, and I think that's really important.
Are there any engineering startups here in Manchester that you know of, like university?
Yeah, there have been spin-outs. Yeah, I know of a couple. There are what's it under the arches called?
The Innovation Centre.
Yes, yeah. So there's the Innovation Centre. What used to be University of Manchester. Yeah, University of Manchester Innovation Centre. Yeah, and that is a sort of a department that's set up to help staff and students to innovate, you know, to commercialise their work if they want to do that, and all of the sort of IP rights, etc. That would sit with a student, but you still get the help. There are some really good sort of student societies. There's the Manchester Entrepreneurial Society as well, which again is a great sort of collection of different students from all three faculties, which is really nice. So yeah, there are spin-outs, and there's support right from, you know, being a first-year student all the way through to, you know, if you stayed and were a postdoc or a member of staff. There's a whole sort of unit that can help you to commercialise and to help you spin out.
Very cool, thank you.
Okay.
Yes, please.
Are 5G signals bad for human health?
Are 5G signals bad for your health? No, I would say. I did it, so there's a professional, our professional institution is called the Institution of Engineering and Technology, and any engineers out there, become a student member, please. I'm the president of it at the minute. And we did a big thing, so that there was quite a lot of press, I don't know, 9-10 months ago, about 5G and 5G signals. And so we put a white paper out as the sort of professional institution. So there's a lot of, and it'll be interesting to get Peter's view on this as well. Peter works a lot on networks and 5G. There's a lot of misinformation out there, a lot of bad press about 5G. I do not think it's harmful. You can, with anything that's wireless, if you crank up the power on something like your cell phone, clearly that's going to be harmful, but that's not what we do. Everything is very low power and getting lower and lower power, certainly in our cell phones. So I don't think it's harmful. What do you think, Peter?
No, I would agree with you. I think the problem is this. I think it's an interesting question, again, back to engineering. You need people who can explain concepts to people who it's not their domain. And you can understand, I remember speaking to my mother, who said she'd seen this in the press, and then you have to find a language, which is a bit why these talks are good, which tries to bridge that to explain how the power of the signal dissipates, etc. We had this back in the 1960s with overhead power lines. But there is good science. And so, for example, when our students work with a radio system, they will have to do a risk assessment. It's good engineering practice. And you will work out the effects of radio frequency energy on the human body as part of the risk assessment process. So no, I think it's one of the, you can see why it's come about.
Yeah.
But this is where we need the professional bodies, as Danielle says, to put out white papers that try and bridge that gap and explain it. Now, but on the other hand, you get people who are radio amateurs who may be using 200 watts of power transmitting to Australia. And I've answered the question in a very different way there. Because the risk assessment will say, no, that could cause heating of the human body. You should do this, this and this. But this is good engineering.
Yeah, absolutely. Yeah. And always good to question it. And when we put sort of white papers out, as Peter said, it's got to be in a language that everybody can understand, because you don't want to make it even more complicated by putting a load of formulas and, but we need to put it in language that everybody understands, and then, links to other things that if you're really interested in it, you can, carry on and find out more.
Oh, I'll come back to you, but if I take a question from the gentleman.
I'll probably get a very similar answer if you think about the AirPods in your ear. Can that lead to brain cancer or something?
No, I guess you can never say never with these things, because AirPods have only been around for a very small amount of time, but they are so well designed, they're so well engineered under very strict health and safety guidance. They are very, very low power. I'm carrying this around. It's Bluetooth connected to my phone over there, my laptop over there. These things are very, very low power in your ears as well. So I don't think there's any health and safety issue with it.
In fact, what I'd say is there's a real trend in the industry now, because one of the things you'll all be most sensitive to is battery life. And what consumes battery life? Transmitting power. So one of the big drivers in our world is to drop the power to increase battery life, which then will make things physically smaller, because the battery's small. You can see all the drivers, which is all heading in the right direction, which is to reduce power. The challenge, as Danielle says, is if you look at something like pacemakers that people have had for their hearts, we've got like a 40-year history. Some of these things, the trick is they're relatively new, so a lot of the risk assessments are very conservative. Yeah,
very, very conservative. Yeah, and as we find out more about them, they might be relaxed, but because we don't have that history like we do with pacemakers, we're very strict on it for now.
Yes, can I come back to you?
With Albert, you said it's 10 times more powerful than Hubble. So, theoretically, would it be possible to have that sort of similar array, but as satellites out of the atmosphere, so you won't have that interference? And if so, what would the challenges be in transmitting the data back to Earth?
Yeah, that's a great question. It would be brilliant to have all of our observatories, radio astronomy observatories, in space, because like you say, you know, you're through the atmosphere, it's completely fine. And the downlink, you know, to get the signals back is a lot easier to handle than the actual signal, you know, because it's so far away, the signal you're trying to get, that sort of very faint cosmic light, and it's radiating at a specific frequency. When you want to send it back to Earth, you can change that frequency. So you can down convert it to a nice easy frequency with a big wavelength, and you know, it's you can, in your downlink, you can do that with. So the challenge is not getting the signal back. The challenge mainly is the cost, because it is so costly, and you can't. It's very difficult unless it's there are people, you know, on board it, or you can send people to it to actually maintain it as well. So there would be some amazing technological challenges to put it up there, but none that are insurmountable, as we've seen, you know, with the other telescopes that are out there. It's a one of cost, so you just have to balance how many do you put on the ground versus how many do you put in space, and at what frequencies. What we find now is, because we can't have a lot of, you know, we can't have all of the telescopes in space, we've got optical, we've got X-ray, we've got gamma ray, we've got radio, you know, so there are lots of different ones in space now, and then lots and lots on the ground. What we find now is that whole astronomy community then work together. So in the past, it was quite siloed, where you'd have sort of the X-ray community, and they wanted to get the best image ever of, you know, a galaxy or, you know, whatever it is. And there's no way they were going to share their stuff with, you know, the radio astronomers. It's not like that at all. Everybody shares. What we tend to do is all observe the same thing. So you might get an X-ray telescope in space and a ground-based radio instrument, all looking at the same thing, and you get such a rich picture, really high resolution picture of something. But yeah, putting things in space, putting everything in space would be amazing, apart from the whole space junk issue as well, which is another challenge. But it's very, very costly as well.
Whilst we have time for one more question, forgive me, because I know people have got to go elsewhere. If I could turn to this gentleman.
So it's all because I suspect that the project now consumes a huge amount of energy, and with the raising energy demand, do you think that we will reach a point where we have to choose between the energy or the information, and if we do, which one do you think that we will choose?
That's a good question. So the amount of, you're saying sort of the amount of energy is growing all the time, sorry, the amount of data is growing all the time, the amount of energy we're going to need would grow with it. So yeah, that's a great question. I think the plan is to make sure that the amount of energy that we need for this growing data reduces. So it's sort of like what Peter was saying before with trying to look at really low power electronics. If you can do that, then the amount of energy that you're going to need decreases. So your data is going to increase. People are looking at all different ways now, you know, hydrogen fuel cells, you know, not just the sort of lithium batteries that maybe we're used to now. But it's all geared towards getting lower and lower power electronics. And that's interesting from a research point of view, because you've got to look at different materials. So I use something called indium phosphide as the semiconductor that I use in my amplifiers, because it's really low power and really low noise. And we cool it to get even lower power and even lower noise. And the chips that we all have in our cell phones, they are gallium arsenide, so it's a different semiconductor material, slightly higher power than the indium phosphide, but really low electronics, really low power. So there's lots of different materials that people are looking at, and they're coming up with new materials all the time. You know, just think about the 2D materials that we do here at Manchester with graphene and other 2D materials. So it's the interesting challenge is thinking of what new material could be out there where you can reduce that, because I think it would be really difficult to reduce the amount of data in the world. So I think it's only going to get bigger and bigger. And if we want to keep up with that, it's the low power materials for the low energy that we need to work on. And there are some amazing material scientists in Manchester working on lots of different materials, very low power stuff as well. So have a look for them, get involved.
Thank you. I'm going to draw it to a close. I know there's some other events this evening.
Oh,
if that's
right.
okay.
Okay. Yeah, of course,
Unless
yeah.
there's a question you want to
No.
yeah, because there's other events going on this evening. Thank you all for coming along. I hope, well actually no, I know that Danielle will have sown some seeds there, and we've got some disruptors have been created if they weren't there before. So would you all join me in thanking Danielle again for a great talk?
Oh, thank you. Thank you. Thank you very much, and great questions. Thank you so much.
Have a very nice evening.